Yeah, I got the email, but I kept forgetting to do it, so I have to do it sometime, maybe today after this class. Yep. Mm-hmm. All right. Well, I think it is 9 o'clock, and it is. It is 9 o'clock. I'm going to get started. So we'll start with the homework assignment. Did you guys get the homework assignment done? Does anyone want me to go over the homework assignment? Yes? No? Yes? Okay. All right. So we'll briefly go over this particular homework assignment, and then we'll have to move on to new stuff because you have your next homework assignment already activated. So depending on how much material we can go over today, I will determine whether we actually have it assigned, which means you have 1 week to finish it once it is assigned. Okay. So with Egg Hunter, the question is in the tar file itself. So let's go ahead and open it up. Oh, okay. I guess I cannot do that. All right. Okay. All right. So once you get the file, oh, I see. Okay. Nope. No, you cannot. I cannot do a mental projection, and you guys cannot see what I see. Reflection. But that's a mirrored image. You have to flip it, right side, left again. Yep. All right. So we'll wait for the screen to come up. So I'm hoping you guys are reading a little bit ahead of me, with the conditional branch instructions, and make sure you review the stuff that you already know about the flags, the compare instruction, the different type of addressing modes that we have talked about up to this point, because you will need all of that for the new homework assignment. Okay? So, but before we go there, let's go ahead and do this particular homework assignment first. And that is in my downloads folder. It's called egghunt.tar.gz. Okay. All right. So the homework assignment is self-described in the text of the homework assignment itself. At a certain point, which is at the label check here, EBX as a register should have that particular value. So the question is, how do we get that? The first thing you want to do is to do a memory layout, a map of how the bytes are initialized from the very beginning all the way up to underscore start. Because, we are not going to utilize the bytes for the instructions, but everything before underscore start, those are the bytes where you can use in order to get EBX to the value that you needed. Okay? So we'll go ahead and get started with this. I will just do everything in line here. Okay? So it's probably okay just like that. The first byte is 12, but that's a decimal number, which means in hexadecimal, as 1 byte, it is 0x0c. Because I want to express everything in hexadecimal, because that's the most convenient representation when it comes to dealing with bytes and bits. Okay? Octal numbers are okay, but they're not nearly as handy. For what reason? Why don't we use octal numbers, and why do we use hexadecimal numbers? It shrinks a little more, okay, but it also lines up exactly, because 1 byte has 2 hexadecimal digits exactly, but 1 byte does not have 3 octal digits exactly, because 3 octal digits will give you 9 bits. So you have that 1 extra bit of the most significant octal digit that's kind of hanging around. It's really hard to combine multiple bytes together when you are dealing with octal numbers. But with hexadecimal, it is very easy to see, oh, this is 1 byte, this is the next byte, and so on. Okay, so this is 0C, and then the next one is a hexadecimal number 1, 2 itself. This one is an octal number, which is 1, 2 in octal, which means we have 1, 8, and 2 ones, which means it is a 10. 10 in hexadecimal is an A. And then we move on to the dot words. Okay, the dot words start with 3, 4 as a base 10 number, or 34. So 34 has 2 16s, and after you take care of the 2 16s, you have a single 2 remaining. But because this is a word, it is 16-bit wide. This is the least significant byte of the 16-bit quantity. The most significant byte is just 0. Okay, it is implied. It is not spelled out. The next one is 34 in hexadecimal, but we also have to remember there's also a most significant byte of all zeros. The next one is 34 in octal. Now 34 in octal means we have 3 8s and 4 1s. Okay, 3 8 add up to 24, plus 4 is 28. 28 as a quantity in base 10 has 1 16, and it has 12 remaining, so we have a C after that. So 1C is 28 in decimal. Are we still doing okay so far with the base conversion? Okay, all right. And then we have the most significant byte, which are all zeros as well. And then we have the label L1. So if I want to spell out here where label L1 is, it's here. Okay, it is after the most significant byte of the last dot word constant. And then we have a whole bunch of dot longs. Each dot long specifies 32 bits or 4 bytes. So now we have 23 in decimal. 23 in decimal is 116 plus 7. So this is 0x17 as the least significant byte. The most significant bytes, now we have 3 additional bytes as the more significant bytes. They're all zeros. Like that. And then we have the 23, which is already in hexadecimal, but this one actually has a whole bunch of leading zeros that are implied, which means the least significant byte is a 23, but then we also have 3 leading, most significant bytes as zeros. And then the last one is 23 as an octal number, which means it is representing the quantity of 2 times 8, which is 16, plus 3, which is 19. 19 as a base 16 number has 1 16 and a 3 remaining, so it's a 0x13, and now we have 3 additional bytes that are the most significant bytes here. So 1, 2, 3, so that is all correct. Okay. Now let's go ahead and make this line a little bit better. Okay, so what I'll do is I'm removing the label itself, and I probably want to change the font a little bit just so that it's easier to read. And I think Control minus may work too. Nope, doesn't work here. Okay, go to View. Oh, come on, Preferences. There we go. So we can change the appearance, change the font to the previous one, which is 11 point. I think that should do it. There we go. Okay, so these are all the bytes that we have laid out in memory. Label L1 is the address of the 17 in hexadecimal. So this is L1, or if you want to, you can make it L1 plus 0. Because that makes it very clear, this is plus 0, the next one is plus 1, the previous one is minus 1. Are we still doing okay so far as how memory is initialized by the dot word, dot byte, and the dot long directives? Okay, so this is really important because what it is illustrating are 2 really important things that will come back again and again. The first thing is there's no boundary. Okay, when you look at the memory layout, once it is initialized, there's no such thing as, oh, but these 4 bytes belong to blah, 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 blah. Nope, there's no such thing. Okay, dot long is just a directive to allocate and initialize 4 bytes at a time. But once those bytes are allocated and initialized, you can access it from anywhere. It doesn't have to be, oh, I have to access the 2-3 from the very beginning of the 2-3. Nope, you can start anywhere you want. And then the second thing is, a label is nothing more than just a symbolic name of a memory location. That's it. Okay? And because the I386 is a byte addressable architecture, that means each byte has a unique address. So at this point, we have L1 as a label. The definition of L1 is the address of the 0x17 byte. Okay? Are there any questions at this point? Okay, if there are no questions, then we move on, because once we know how memory is laid out, the first thing we want to do is to say, okay, what do we put into EAX so that EBX eventually will end up with this decimal number here? Okay, The first thing is to convert its decimal number into hexadecimal number, okay? Because that will give me a representation of the kind of the binary bit pattern, but except I don't have to use all zeros and ones. And to do that, you can choose one of several ways. I just use GDB for everything. It's kind of my Swiss Army knife because it's really useful. So to calculate or to figure out the hexadecimal representation of that number, you just say print /x, which is in hexadecimal, and then you can select this, copy, and then go to here and paste. Now I know you guys are not using Linux. You're not using the Xterm or the terminal program that I'm using. But if you use PuTTY, you can pretty much copy and paste across your terminals as well. Okay. So you are strongly recommended to use PuTTY because you can open up as many terminals as you need when you work on your homework assignment. So this is the pattern that we want to be in EBX when everything is done. So what I'll do is I'm going to copy this from here, go back to the program, and paste it, just somewhere. Okay. Oh, nope. Paste. Okay, there we go. And of course, these are all, inside comments because otherwise they'll be interfering with the compiling or the assembling of the program. Are we still doing okay so far? Because what we want is this value in EBX. So I'm just, moving it over here so that we can group all the related stuff together. All right. Looking at the instructions that we have, let me turn on, well, I don't want to turn on line numbers. Well, maybe it's okay. Let's see. Okay, line numbers are fine because I just don't want it to push and make lines wrap around too much. So when you look at lines 12 to line 15, which instruction, if there's only one, can set the most significant 16 bits of EBX? There's only, how many instructions can do that? One. There's only one instruction that can set the most significant 16-bit of EBX. And that would be line 13. Okay? Line 13 is the only one because line 13 says move L, move long, and long is 32-bit wide. From some source, okay, it's indirect EAX, we'll deal with that later. The destination is what we care about because the destination of line 13 is EBX. All of the other instructions that has B something as a destination, they can only change the least significant 16-bit or somewhere within the least significant 16 bits. Okay, so the only chance we have to set the most significant bytes, the 2 bytes that are most significant in EBX, is line 13. So what I'll do is I'll just write down here and say only chance to set 0x1700 to bit 16 to 31 of EBX. Is that making any sense? So what I'm doing is I am looking at the end result that I need and try to go backwards and figure out, okay, I want the most I want to define all the constraints first, okay? Because once you have defined all the constraints, you may find out that there's nothing else to think about, okay? Because the constraints already tell you this is the only way to do it, okay? So now that I have identified 1700 is going to be the most significant 2 bytes of EBX, now I look through the memory that is already initialized and say, do we see oh, by the way, 1700 means 17 is the more significant of the 2 bytes and 00 is the less significant of the 2 bytes. So when we are searching for this in memory, because memory is listed from left to right, low memory location to high memory location, but the highlighted portion is a number where we write the most significant digit first on the left-hand side. So that means the byte pattern that we are looking for is not 1700. Is 0017. 00 being the byte that has the lower address, and 17 being the byte that has the higher address. Okay? And it doesn't take long to find that because we only really have one pattern that is here. Okay? So we go, okay, so we have identified the 2 bytes that we want to put into the most significant 2 bytes of EBX. But you cannot just change the most significant 2 bytes of EBX, because every time you move something into EBX, you're always moving how many bytes? 4 bytes. And these are not the first 2 bytes, because these are the third and the fourth byte that you're moving. Which 2 are the first 2? The ones to the left-hand side, okay? So that means we need this byte to be the second, but this is the second byte. This is actually the first byte that you have to move. So we are talking about these 4 bytes that you need to move into EBX, starting with this one here. Now, because 17 is L1 plus 0, it makes this one L1 minus 1, L1 minus 2, and this is L1 minus 3. Okay? In other words, we want to copy the 4 bytes starting at L1 minus 3 into EBX on line 13. Then you look at line 13, and line 13 does not give you any flexibility because it's just saying we are going to use EAX as a pointer. So that means there's nothing you can do on line 13, but you can do something about EAX on line 12. So on line 12, the objective is we want EAX to end up with L1 minus 3. And how do we do that? It's already move immediate, which is the right addressing mode. So we just have to say L1 minus 3 here, put it into EAX. Okay? I don't have enough time in this class, but if I were actually doing this homework assignment, I would comment out line 14 and line 15, test the program just to make sure that by the time I execute line 13, EBX does end up with the correct bit pattern as the most significant 16 bits. So I would check that first, because otherwise, if the program doesn't work, then I would have other suspicion of why it's not working. Is that okay so far? Yep. Yeah, I have to comment out line 3 too, because otherwise it would not compile. Okay. But since I don't have enough time, today, I'm not going to do the step-by-step testing. But if you guys when you guys are working on the homework assignment, it really helps to kind of debug it line by line. Yep, go ahead. Yes, you can.
You're going to see what's done.
Yeah.
So you don't have to comment out 14 or 15.
It won't compile. It will not assemble.
Oh, yeah.
Yeah, that's the only thing. Yeah. Yep. Because if it doesn't assemble, you cannot run it. Yep. All right. So I'm fairly sure this is going to get the job done. So the next question is, what do I want to put into BX? So what you want to do is to say, what is the constraint here? I want to identify the constraint so that I limit my options here. So you look at BX, and then you look at the next instruction, which will move into BH. Okay. So once you understand how BL, BH, BX, and EBX are related, then you go well, line 14 is the only chance to get BL initialized. Okay. We have a chance to overwrite BH again in the next instruction, so I'm not too concerned about it. But line 14 is the only chance to set the least significant byte of EBX. Okay? So now the question is, what is it supposed to be? Well, it is the least significant byte of EBX, so it is supposed to be a 1C. You look through this pattern here. I see 1C over here. This is L1 plus 0, L1 minus 1. This is L1 minus 2. So that means, I just need to specify L1 minus 2 over here. Because the addressing mode is already a direct addressing mode, which means whatever expression I specify as the first operand is going to specify the location where I copy, in this case, 2 bytes to BX. Okay? Oops. Is that correct? Yes, it is correct, because 1C is going to the least significant byte of EBX, or just BX or BL. Okay, so this is okay. I don't really care about this byte here, okay, because this is going to be overwritten anyway by the next instruction. Line 15 is a little bit tricky, because instead of using the direct addressing mode, I'm using the immediate addressing mode. So in this case, I want to change BH to a 1-2, okay, because that's the final result. And you look through the memory here and go like, oh, okay, we can see that there's only exactly one 2 here, and it is L1 minus 1, 2, 3, 4, 5, 6, 7, 8. But if you specify L1 minus 8, it's not going to work. Okay? You get a warning. Okay, so let's do that first, okay, because I want to show you. Okay, it doesn't work, and the compiler or the assembler will actually give you a warning and say, this doesn't make any sense, okay? So we'll go ahead and try this first because it seems like, we could do that with bx. Maybe the $ is not important in this case and we can use the same approach, okay? So I'm just going to save the file first and go ahead and try to assemble the program, which is not going to work very well because it's going to complain. It's not complaining. It's not complaining. The linker complains? Oh, because the linker is the one that has to resolve the expressions. Even though it's completely resolvable by this point, it's not 100% resolvable. Because at this point, okay, this deserves a little bit explaining, because if it startles me or if it stumps me for just a fraction of a second, it is still worth mentioning. The reason why it's not complaining at this point is the assembler really doesn't know where L1 is. It is really just saying, oh, within this portion of this entire program, L1 relative to the beginning of this particular object file is here. Okay? But what does that mean? If you look at the file bunny.s, L1 relative to the beginning of this entire thing is, okay, this is location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So as far as the assembler is concerned, the only thing it knows is L1 is 9 bytes from the beginning of this particular object file. Is that okay? So it's just a 9. Okay, it's 9, but with a tag to say that it might change, it might get relocated later. So if L1 is 9, what is L1 minus 8? 1, okay. Can we represent 1 using just 1 byte? Yeah. So that's why the assembler is not complaining, because the assembler says, well, L1 as it is now, okay, it can change, it can get relocated later, but as it is now, we don't have a problem. Okay, it can still be represented using a byte. So that's why on the line, on the move byte instruction, the first operand, it's not complaining yet, because we still have sufficient bits to represent the value that we need to represent. Is that okay so far? Does everybody kind of understand why it's not complaining yet? Okay. Now, on the other hand, okay, I just want to make this program does complain about stuff. On the other hand, this is an instruction that really should not be here, but I'm going to put it here just so that we can see the error message from the assembler itself. On the other hand, if you spell out an exact value that cannot be represented using a byte, like 1000, then the assembler has all the information to complain and say, hey, this cannot happen. I cannot represent 1000 as a value using only 8 bits. So we'll go ahead and save this program, which is not the actual program, but that's why it truncates, quote unquote, truncates right now, because 1000 represented as a hexadecimal number is 3E8, which means it requires more than 1 byte to represent. But in this case, the assembler can catch it because 1000 is spelled out as a constant. It does not depend on relocation and the linker to determine the actual value of 1000. On the other hand, L1 itself is quote unquote a floating label, which means I know where it is relative to the beginning of this entire object file, but I still don't know how it relates to the beginning, where it is actually going to be located when everything is linked. Okay, so that's why it cannot complain about this line just yet. Okay, so let's go ahead and reassemble, and this time we'll relink. As we relink, then the linker is going to complain because the linker is the one that actually determines where we want to put each object file. And at this point, it knows that the address of L1 is going to require more than 1 byte to represent. And as a result, the linker is the one that complains and go like, hey, we have a problem here because you have a move byte instruction, but the constant is going to require more than 8 bits to represent. but it's still a warning message. It is not an error message, which means the executable bunny should be actually created, even though it doesn't. Nope, actually it doesn't do it, which is even better. All right, so if this is not working, then we have to go back to this instruction to go like, I wonder what it should be. Well, since it's already move immediate, you just specify whatever you need to go into BH. It's move immediate. It's not move indirect or move direct. Okay, so we want a 1, 2 to be there because it is this particular byte here. We want that to be in BH. Well, we just specify 0x12, save the file, reassemble, relink, and now we can run the program. Bunny. And if I'm brave enough, I can put a breakpoint on line 19 or check here. By the way, you can set breakpoints based on the name of a label. Run the program, and then we can use IR EBX, info register EBX, to look at the content of EBX. So we can double check that in base 10 it is the correct number. In base 16 it is also the right number. So that's confirmation that the program is doing what it is supposed to. Are there any questions about this particular program? No? Yep, go ahead. Yeah, you can use the print command too. You can say print /x, $EBX, it will do about the same thing. There are usually quite a few ways to do the same thing. It's just, which way is, more handy sometimes. The info register option gives you both the base 10 and the base 16 representation at the same time. All right, so that's your homework assignment due today. And your new homework assignment is already here. I changed the name a little bit from last year. It's called Monkey Business. And of course, I have to include a picture, just so that it's so that you guys can focus on the monkey instead of the homework assignment. All right. So let me go describe what this homework assignment is supposed to do. Okay, it's kind of like string. Okay, there's a C function called string. It finds a substring within a string. Okay, so it's kind of like that, except you have to do everything in assembly. Okay, all right. So let me do this first. Okay, so I'm gonna. Okay, where's the Z? Alrighty. When I specified the tar file, I forgot to type in the G. I suppose I can change the name of this. Okay, yeah, let me change it first so that you guys don't get an inconsistent file extension. So let me go here, change it to GZ, update. There we go. That's easy enough. All right, so the homework assignment has the right file name now. Let me save it first because sometimes I forget to save and then the change is not effective. There you go. Okay, so now it has a GZ. All right, so let's go ahead and take a look at this homework assignment. It's tar zzvf in my downloads folder because it's already downloaded without the Z, so it's just going to be G itself. It still works because in Linux, the extension of a file doesn't really matter. Okay, I could have named this .txt. It will still work the same way. Okay. So you go to the subfolder called monkey biz, okay, and look at the file called monkey. And this one doesn't give you a whole lot of stuff, okay, to start with. Okay, it has a .fill. Okay, a .fill, I can tell you exactly what it does. It simply allocates 256 bytes, initialize all those bytes to zeros. That's all it does. Okay. And then we have underscore start as a label, and then we have check here as a label. All of your code has to fit between underscore start and check here. Obviously, you won't be doing it in 3 lines of code, but you will be using more lines of code. Just do it between those 2 labels. So in other words, you can insert as many lines as you need to between underscore start as a label definition and check here as a label definition. All your code has to go there. But what you're going to do is to do what is described here. So what you need to do is by the time we get to check here, EBX, okay, I think it's supposed to be EBX. Okay, EBX then. So EBX should point to the memory location of 5 bytes. Well, that's not 5 bytes, is it? Last year it was 5 bytes. This year there are 7 bytes. It's coconut. Okay? 7 bytes. So change this 5 to 7. So we want to find coconut within whatever content is going to be initialized within these 256 bytes. To test this program, I will initialize the 256 bytes starting at L1 with a test case, with certain test cases. Then I'll run the code, stop and check here, and see if the address in EBX is correct. So note that this program has sufficient complexity that most implementations should be different from one another. I can tell whether a program is artificially altered just to look different. So please work on your own program and do not share code. Okay. Well, I put it here because in past semesters there have been situations where submissions were not original. I mean, I can see certain people work together, which is not a problem, but it does end up with not independent work to be submitted. Okay. All right. Okay, so let's go ahead and find out, how to test this program and also, how to get started with this program. All right. So, I give you the instructions to unzip the file. This is rezipping the file, once it is all done. And it mentions EDX here. That should be EBX. So let me change all of that stuff first. I changed one, but not the other version, so I have to fix that first. EDX should be EBX. I'm fixing it now, because I don't want to do it later and then forget. All right. Okay, that should be it. Save and display. All right. So the way you want to test your program, this is the important part, okay? Because up to this point, we have not done anything like this. So what you want to do is to create at least one, but I think you should define or have multiple test files. So a test file would be one, that either has the word coconut in it or not have the word coconut in it. When you're testing your program, these are the commands that you need to run in GDB in order to initialize those 256 bytes with the content of the text file. So I'm going to go through this exactly to show you what you need to do to test this particular program. Okay. All right. So getting back to the terminal. Okay. That's not much going on here, and the only thing I'm going to do is to put a no op instruction here, just so that I have a place to stop to show you the content of the memory at L1. Okay. And then I will have 2 test files. I'll have test0.txt. Once again, the extension or the name is not important as long as you use it correctly or consistently. So I would say here and go Donkey Kong likes coconuts. Okay, so the word coconut is in here. Okay, that's one file. And the other file is DD Kong. Is it D-I-D-I or D-E-E-D-E-E? Huh? D-I-D-D-Y. Diddy Kong. The fact that you know that is speaks volumes. Likes bananas. Now that one I know as well because I also play, what's the name? Smash Bro. And he throws bananas, right? Okay, so this file does not have the word coconut. Okay, so save it. Okay, now we can actually assemble first. Assemble monkey.o, monkey.s. There we go. Link it. Now, for this particular program, there is nothing you have to do in order to link and assemble and link the program so that it can at least run. And then we run the program in GDB, like so. List the program, not a whole lot of stuff going on. Put a breakpoint on _start, which is the no op instruction, and then run the program. First thing I want to do is to say, hey, show me the 256 bytes located starting at label L1. Okay, we remember the X command, right? So X/256 items. Each one is a byte, and I want to display each byte as a hexadecimal number, X here. And then you specify the address, and remember you don't want to use label L1 all by itself as an address. You have to say the address of L1. It has to do with a misunderstanding between GDB and what the label is. Okay, so it shows you not very interesting stuff. A whole bunch of zeros is what it shows you. Okay. Are there any questions at this point? So the next thing we do is we utilize this particular command in GDB, which is restore a file name binary into &L1. So we say restore test 0 first. Okay, this is Donkey Kong. Test0.txt binary into location L1. Press the enter key. It says something about restoring binary file blah 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 into memory. Don't be alarmed, even though the file itself is a text file. It always says it's a binary file, okay, which is okay, not a problem. Then we want to go through the same command and take a look at that chunk of memory using the X command just to see whether it is still all zeros, okay? So we press the enter key and we see, hey, there's a whole bunch of non-zeros here now. There's a 4, a 6F, a 6E, a 6B, blah, 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 blah. And, there's a 0A, which is the line feed character. So you can kind of tell that this looks like a text file from the bytes, but you don't really know the content of the bytes. Okay, fine. Let's go ahead and find out how to do this a little bit better. And I forget all the options of X, so I'm going to say help X to help remind me how to look at the ASCII code of characters. And if you look through this part here, there's a C option. So instead of using X, which displays the content of a byte in hexadecimal, you can interpret those bytes as characters using a C in place of the X. So what I'll do is I'm going to rerun the X command, but this time change the X to a C, and you can see the first part of the memory that is initialized is in fact DONKEY, Donkey Kong likes coconuts. Okay? Are there any questions about this test file? Yep.
So if you would have had your text file at capital C, would not have found that.
Then you should not have found it, correct, because it is case-sensitive matching. Yep. All right. So then you run your program. Okay. You want to put a breakpoint. Okay. You want to put a breakpoint at check here. Then you continue to run the program until the checkpoint. And you want to say, do a print EBX and see if EBX is telling you where coconut is starting. If it is found, if it is not found, it is supposed to be a 0. Now, obviously, this program doesn't do quite that because I don't actually have any code to do the search and setting of the EBX. Are there any questions about this homework assignment? The nature of the homework assignment. Okay. So if you want to change the test case and run the program again, it's okay. Because every time you run the program from the beginning, which will get a warning if you have not finished the program execution, you just say yes. But every time you start, the content at L1, they'll all be reset to 0 to begin with. So every time you run, you can use restore as a command to reload a new test case, or you can reload the same test case if you want to into this chunk of memory. Are there any questions about how to test your program? No questions? All right. So if there are no questions, then we're going to go into the actual, part of the program, and we'll try to figure out, what to do with this. Okay. The first thing you might want to do is to come up with the pseudocode to do it. Okay. Because what you need to do is to search for the word coconut. Okay, you have to search for the bytes or the characters, COCONUT. Okay, and you have to do it in assembly code. So now we want to go back into the conditional branch instructions because that's the one missing piece that we have not really finished talking that you will need in order to do this. Okay. All right. Well, there are a few pieces, but we have talked about almost all of the pieces. We just have not connected all of the pieces at this point. So getting back here, there are several things. Okay, arithmetic operations, older but still useful. This link actually will give you the instructions. It will give you the add instruction, the subtract instruction, and also the compare instruction. I checked. It is tucked away at a really small place, but it is there. So I will show you exactly where first. Okay, so it's tucked away here. Common instructions that affect the status flag. So here's the add instruction. We haven't really talked about add with carry. It is not important for this homework assignment. We have talked about subtract and also compare. So all of those discussion, that we went through last time on Tuesday is here. Okay, so this is where you can find all of that information. I just want to let you know. But getting back to the homework assignment, where's the description? Branch instructions, jump instructions. This is where we left off last time, are the conditional branch instructions. So what I want to do is to show you an example. Let's take a look at one particular conditional branch instruction first. Okay, we talked about unconditional branch, which is just continuing execution of a label regardless of how the flags are set up. So that one is done. But we do want to talk about a conditional branch instruction. There's a whole bunch of these. Okay, there's JC, which means jump if and only if the carry flag is set. JNC, which is jump if and only if the carry flag is cleared, and so on. So I'm just going to focus on one, because the rest, they behave about the same way. They just look at different flags and a different polarity. Okay, jump. Some will branch when the flag is set. Some will branch if the flag is cleared. Okay. All right. So we'll go ahead and write a very simple program to illustrate JC. Okay. So we'll go to this folder and write a new file called jc.s, and we'll have a dot text. Yep. Is the carry and yes, yeah. So B and C refer to the same flag. Yep. And B can also be interpreted as below. It comes in handy when you compare. Okay, so what we want to do is, I don't want to give away too much of the homework assignment, so I'm going to do it in a way that does not give away too much of the homework assignment. So I'll just move a particular value, let's say 200, into an 8-bit register. So BL, is just as good as any other 8-bit registers. Okay. Add byte. Okay, so here's a question. I think most of you know the answer already. What is the smallest value I can specify here in order to end up with a carry being set? What is the smallest value I can specify here so that this instruction as a whole will set the carry flag? Nope. 56. Why? Why 56? Why do I use 56 as the smallest value so that I can end up with a carry flag being set?
Because you have the field 256 initializes the first 256.
Okay, in an unsigned interpretation, what is the largest value you can represent in 8 bits? 255, exactly. Okay, so 256 is the first value that cannot be represented using only 8 bits. And that's why if I add 56 to 200, I end up with a value of 256, which cannot be represented unsigned using 8 bits. And that's why the carry flag will be set. Now, if I change 56 to 55, it won't be set. Okay, the carry flag will not be set in that case because 255 is still it can still be represented as an unsigned number using only 8 bits. Okay, all right. Are there any questions about this part here? Okay, if there are no questions, what I'll do is I am going to use a conditional branch here, a JC, and say if the carry flag is in fact set, I want to go to label L2. Okay. And I define L2 down here, and L2 is not going to do anything. But in order to differentiate between the case that actually did a branch or not, okay, if I do something like this, it's not going to be able to tell the difference. Because whether I did the conditional branch to L2, which is the no-op instruction, or did not do the conditional branch, which means I just execute the next instruction, in both cases, it will be the no-op instruction. Is that making any sense? So that's why in order to differentiate whether I did the branch or not, I need to insert additional instructions here just so that I can tell whether after the JC instruction, I end up on line 7 or I end up on line 11. Okay? Which is kind of coincidental, 7-11. No, really, it is coincidental. I did not plan for this to happen. All right. So this is the program that I'm writing. And what do you guys think? When I single step on line 6, should I end up on line 7 or should I end up on line 11? 11. Yep, exactly. Because the carry flag should be set. And as a result, branch, if and only if carry is set, should go to the label L2. Okay? All right, so let's go ahead and assemble link and GDB and put a breakpoint on exactly line, well, I want to put a breakpoint on line 5, okay, just so that we can see what's going to happen with these instructions. Okay, run the program from the beginning. We have already ran the instruction on line 4, and I can do a print /x $BL, okay. BL has C8. Well, is that really 200? You can double check, okay? What is 12 times 16 plus 8? Okay, so we have 16 times 12, 192, and then plus a 12, right? Is it plus 8, okay. So plus 8 is exactly 200, okay? So I'm just double checking to make sure that, in hexadecimal, this is in fact, 200. Okay. All right. So BL has the right value, and the next thing I want to do is to say, oh, tell me what is BL plus 56. Okay. And it says, hey, it's 0. Does that make any sense to you? Yep.
Does printing anything will set up any flags?
No. Yeah, when you print something, it does not actually use the quote-unquote instructions in your program. As a result, the flags do not get changed when you're printing. So you can basically mess around with the registers, do calculations and whatnot. It's not going to change the flags. Okay. All right, so we'll go ahead and single step. Okay, so single step meaning we are executing line 5. And now we want to print what is in BL again. And what do you think should be in BL at this point? 0. Very good. And if I say IRE flags, what should I see? The carry flag is set, okay? What about the other flags? Let's just go through the exercise again, okay? What about the overflow flag? Should be cleared. What about the 0 flag? Should be set because the end result is a 0, okay? There's one more left, which is the sign flag. What about the sign flag? Should it be set or cleared? Cleared because 0 is all zeros, and the sign flag is nothing more than the most significant bit of the result. Okay, so IRE flags, and we can definitely confirm that the carry flag and the 0 flag are set. The other 2 flags that we are interested in are cleared. Okay, very good. Okay, so this is the moment of truth because we are on line 6. Either we go to line 7 or we go to line 11, right? And single step gets us to line 11 in this case, which means the conditional branch actually changed the path of execution. Okay, that's great. But if I were you studying for this class, reading my notes and stuff like that, I would just spend a little bit of time, go back here, change the 56 to back to 55, because in this case, the carry flag would not set. It would be cleared, and as a result, execution would just continue with whatever instruction is right next to the JC instruction. Yep. Yeah, case sensitive. Yep. So after we change this program, just a little bit, right? We'll go back here and say reassemble, relink, and re-GDB the program. Put a breakpoint on line 6 this time. Okay, run the program. We are on line 6. but I still want to know what is in BL. What do you think should be in BL at this point? If I say print without /x, which means it's going to display the content as a signed decimal interpretation of the bit pattern, what do you think it should be printing this time? Okay, we know the bit pattern, right? We know the bit pattern will be all ones. But since this is going to be the signed interpretation of those zeros and ones, it's -1. That's right, because if it is signed interpretation, all ones is representing the value of -1. Very good, okay? All right, but we also want to look at all the flags because we want to see, hey, tell me all the flags. But before I press the enter key, once again, we want to think about this and say, okay, what do I think would be set and what do I think will be cleared? Let's start with the carry flag. Cleared. The Z flag, cleared. Overflow flag, cleared. And what about the sign flag? Set. Okay, so the sign flag is the only one that should be set. Everything else should be cleared. And that really is the case because we can see the sign flag is set, but the other 3 flags that we care about are all cleared because they do not show up here. Okay, very good. Moment of truth. Okay, single step. We think it should continue execution on line 7 and not on line 11 because the branch is not going to happen. And that really is the case. Okay, so when I'm studying for this class, I would go through simple experiments like this. Okay, even if I have a pretty good idea that I understand all the concepts, it doesn't take much time, and yet, it is a good confirmation. You just single step everything and go like, okay, it works the way it's supposed to be working. Are there any questions? No questions? That means you have all the pieces that you need to do the homework assignment. Okay, how would you do this? I mean, this is a homework assignment, and you are actually going to write a program to do this. So how are you going to do this? Okay, let's see. All right, so what we'll do, or what I'm going to do, is to go back to the folder and take a look at the source code again. And then we say, we are supposed to find the pattern COCONUT in this particular, in the space, in the 256 bytes between label L1, from label L1 to L1 plus 256, basically. What would you need in order to get this program to work? So the first thing you want to do is not to think in assembly code, not to think in mnemonics, and not to think in, we need this instruction, we need that addressing mode and stuff like that. Now, some of you may be able to do that, okay, and you can go ahead and do it that way. But in general, it's better to look at this program and go like, well, how would I write this program in C++? Okay, I would start with that. Okay, so if you are to work with this kind of program as a C++ program, then we'll have a monkey.cpp as a C++ program, right? And we'll have a main function, just the usual stuff that you already know. We have a character array. So in this case, I will have an initialized array, and we'll just say, well, in that case, we can make it a const char. Text, okay? And we just say this is monkeys like coconuts. Okay, all right. So that's the initialization of the string or the array called text, okay? And then we can go ahead and use the rest of this program to figure out, okay, how do we know whether coconut is in this string or not? Actually, I take it back. This is not the best way to do it because we want to make it length delimited and not null terminated, okay? Well, either way is okay, so you can kind of choose either way. All right, so how do we get this program to work? What would you do to search and see if you can find coconut in it? If you can find coconut, I want basically a pointer to end up pointing to the first byte of coconut. If not, I want that pointer to be a null pointer, to be 0, okay? Okay. Is this helping? I think this is giving away a huge clue to your homework assignment. Why do you think I picked the name EBX? Because EBX is going to be the one pointing to the first byte of coconut, right? Okay. Let's see. You can define other registers too, but remember this is a plain C++ program, okay? It really is not your actual program. And then what do you do about this program? What you want to initialize, right? Okay, so you want to say EBX becomes the beginning point, the start of the array. Okay, all right, so we can do that. Now this, if you want to do something like this, you kind of have to have const char also over here, because otherwise the compiler will complain one is const and the other one is not. Okay, and then what do you do? Okay, do we need some kind of a loop? Okay, I think we need some kind of a loop. But in the loop, what are we going to do? We have to compare what EBX points to the first byte of coconut, then the second byte of coconut, then the third byte of coconut, until we confirm all 7 characters. Then we say, yep, it's found. What if it's not found? Increment EBX and start all over again. Is that making any sense? Okay, so there are so many ways to do this, even in C++. Okay, so we can do it in any one of these different ways. Okay, all right. So let's go ahead and see if we can. Okay, in C++ I can do this. Okay, yeah. It may not be the best way to do it because you cannot do this in assembly. There's no such thing as while in assembly, so you have to kind of think about what to do with the instruction that you have to implement a while. Or you can read the notes ahead of you to figure out a systematic way to do it. Okay. All right. So as long as EBX is not null, which means we have worked past the end of the string itself, what do? I think we need a whole bunch of compares, right? So you can say if, okay, I'll do one version that is easy to translate. Okay, so we say, okay, if EBX points to a character and it turns out to be C, then we do the following. And once we know it is a C, then we say increment. Let's go ahead and add 1 to EBX. Okay, so we say EBX increment. Okay, you can increment a pointer, right? Huh? Yes. Because the const part is not about the pointer, it is what it points to. Okay, that's a very good question. Okay, because when we use the word const, there are at least 2 places where we can put a const here. Okay, in this case, EBX is a pointer to a character that is not supposed to change. But what about the pointer itself? Can it change? Yes, you just cannot change what it points to. Okay, so the destination cannot be changed, but you can change the pointer itself. Okay, but that's a good question. I like that. So the next question, once we know that the first character that it points to is in fact a C, then the next thing we do is to say, is the next thing an O? Okay. Okay, so I'll just do a part of this because it gets really boring after a while. And I'm going to turn on auto indent so I don't have to do all this. Okay, there we go. So we say, oh, okay, the O is matched. We want to look at the next one. So is the next one another C? If so, then we look for the last O because, as I said, I don't want to go the entire way. I just want to confirm cocoa and not coconut. So we have to first increment EBX and confirm the last one is O. Okay, so if cocoa is what I'm looking for, then this is not going to be the answer, right? What do I need to do? Because right now EBX points to the last character that I'm looking for, not the first. So how do I rewind it so it works? Yep, subtract how much? Not 4, 3, because we are pointing to the last character already. I wanted to point to the first one. So EBX minus equal 3 is going to be okay. And we also want to break out of the loop. Okay? In fact, well, I'm not going to do it just yet, but okay, so I can break here. Now, what about all the else cases? What about this else here? What does it mean? What does it mean I can find COC, but then the next one is not an O? I have to go back and continue, right? Well, that part is up to you. So I have to do something about the pointer. So, okay, so I'm going to write down here. Do something about EBX so we can continue the search. So where do you continue the search is? The letter C, which C? There are two. The first one? Yeah, you can do it that way. That's a safe way to do it. Okay. So I will let you guys choose, how to do this part here. But whatever you do after that, you have to use a continue because it's time for the next iteration. Is that making any sense? Okay. But everything has an else case. What about the else of this guy here? I'm just going to do the same thing here. Now remember, this do something may not be the same as the other do something. Because at this point, okay, if you look at this else, okay, the case that we're in at this point, the then is basically matching the C, not the O. So we failed to match the second C of Cocoa at this point. And where should you rewind EBX to continue the search of CocoaNut? You have to think about it, okay? But the amount of rewinding can be different. That's all I'm saying, okay? But this in return is the then part of another conditional statement. So when you look at this part here, you look at the end of this, and then you say, oh, we have another else here as well. What are we going to do? Something similar, but not exactly the same. You have to readjust EBX and then continue with the loop. But how much and how you adjust EBX depends on, where you are at that point. And this whole thing is also the else or the then portion of the first if. So obviously it also has an else. And you have to determine how to continue the search. Is that okay so far? Does everybody kind of get the idea of what we need to do? Okay? Sort of? Yes? No? Maybe? Okay. Okay. But TAC, you haven't really talked about anything like this. Okay? Well, let's find out what we can do about these constructs in C++ and how they map to constructs in assembly language programming. We'll start with EBX equals text. Okay? Do we know how to do this or the equivalent of this in assembly? Yep. No, this is not compare yet. You are going to set the variable EBX to the beginning of the entire array. In your program, where's the beginning? L1, and you have a register called EBX. Okay, well, that sounds okay. That's the easy one. What about a while loop? Okay, a while loop is a pre-checking loop, right? Which means we check the condition first before we go into the body of the loop. So what is this saying? While asterisk EBX. What does it do? It compares. Okay, what is it comparing? No, it's not about the address. The value at EBX, right? Because the asterisk is the dereference operator, which means we use EBX, which is a pointer, as an address. We go to that location and say, hey, look at this byte over here. How do I know that's a byte? What is the type of EBX here? It's a char pointer, which means it points to a char, a byte, exactly. Okay, so we compare that byte to what? To 0. And if it is no, well, okay. We compare it to 0, but under what condition do I stay in the loop? When it is not 0. Very good. Okay, so when it's not 0, we stay in the loop, which also means if it is 0, we get out of the loop. Okay, well, if that is the case, maybe I can rewrite this in a way that is more friendly to assembly language programming, but your other professors will cringe and go like, ew. You know? Okay, so we'll say if EBX does not equal to 0, go to and while. Now, do not ever do this to your other classes because you will get points dinged for sure. If there's any point left to ding, that is. Because the use of go to in any other class other than this class is a super bad idea. Okay, if you do that at work, you know, some really bad things will happen too. So this is not just at school. Oh, you know, I have really picky professors who do not use go-tos. You do this at work, you will get into big trouble as well. Okay, okay. But in this class, we have no option. Okay, because we do need that sort of thing. But what I want to do is go back to this instruction here and say, can we do this in assembly? Just focus on one line, line 7. Can we use several instructions perhaps to do one line of C++? Can we compare what EBX points to a 0? And if it does not, well, actually, I got the polarity wrong. Okay, if it is 0, go to and while. Okay, can we do this in assembly? Yeah, but you can also use. Okay, which flag should we look at? The 0 flag, exactly. So if the 0 flag is set, we branch to a label called and while. Okay, but this is only one part of a loop, right? What makes a loop instead of a conditional statement? At the end, we always go back to the beginning. All right. Okay, so that means this is the end of the loop. We should be going back to loop or begin while. Okay, just to be more consistent with my labeling. And where should I define begin while? Right before the if is perfect. Okay, so begin while is here because at the end of each loop you have to go back and reevaluate the condition to see if you have another iteration. So that is correct. Okay, very good. Do we know how to define labels in assembly language programming? What does it look like? Exactly, just like that. Very good. Okay, so we have some idea of how to do this now. Okay, great. We have something here that doesn't seem to be mapping to anything that we can do in assembly. There's no such thing as break in assembly language programming. But what does break do in C++ programming? For those of you who have been exposed to this. Jumps, exit the loop, right? Gets out of a loop. But we don't have break in assembly language programming. What do? Jump to and while, because and while is a label that defines the end of the whole thing. Oh, okay. So we have go to and while here. Okay. So the same applies to all the other break if you have other break. Okay. What about continue? What does continue do in the loop? Exactly. Okay. So all the continues basically are go to begin while. Okay. And the other continues are the same because they're in the same loop. So I'm only going to do one. Something is still missing. We don't have else in assembly language programming. So what do we do about those? Sorry?
Like
JNL is not going to do it, okay? Because it's still a conditional branch, but we don't need a conditional branch. So what I'll do is I'm going to do one of these, and then you guys can tell me what to do about this one. So let's just focus on the code between line 19 and line 28 at this point, okay? Because it will get longer, okay? All right, so this is basically saying, okay, I don't even care about the context of this code. I just want to convert the code from line 19 to line 28 into assembly code that we know of, okay? particularly the control structure. What do we do? What does it mean when we say if asterisk EBX equals, quote, lowercase o, end quote, close paren, blah, 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 blah. It's a conditional statement, right? We're trying to decide which way to go. Is that right? Okay. So that means if this is false, if this condition is not true, then we have to go to here, right? If this condition is in fact true, then we start here and continue with the other instructions, the other stuff that we have to do. Okay. We need a what? We need a conditional branch. Okay, very good. Okay, so we know how to do the equality check, but if you want to do this in assembly, it helps to flip the equality to non-equality. And then you say go to, I'll call this else 1 here because I cannot use just else. So then I would define this as else 1 colon. In other words, I am turning a structured program into a non-structured program. Is that okay? Okay, let's think about this here. Okay, from line 19 to line 28, is it still doing what it used to do? But can we convert like line 19 into assembly instructions? It has a compare, and based on equal versus not equal, it goes to a label. Can we do that in assembly code? We look at line 24. Can we do that in assembly? Okay. Now, there's only one thing you have to be really careful about that I have not really, well, that does not need to be taken care of here, but in general you do. Because if line 22, well, let me just go to line 22 first. If line 22 is not a go-to itself, then you have to be extra careful because after line 22, it will fall through and it will go to line 27. Is that making any sense? You have to skip the else. Exactly. So technically speaking, okay, you have to go to and if 1 and then define and if 1 to be here. Now, in this case, it doesn't need that because line 22 itself is a go-to. It is not conditional. And you're just continuing execution at end while anyway. So that's why you do not really need a go-to and if 1. But if this is a normal, just a general conditional statement, you need to go around the else case after, at the end of the then case, you have to get around the else case. Is that okay? All right. So do you think you can work on this program now? Okay. So the key is to write it in C++ first. Okay. Get the logic done. Make sure you know how many bytes to rewind in each case, when to get all the way to the end of the loop and get out, when to go back to the beginning to start the next iteration. So you want to test all of those things first in C++ because you already know C++. Okay? So you want to start with something that you're familiar with. And once you get your C++ program to work 100%, then you start to look into that code and go like, okay, now how do we convert it into assembly language? Okay? That's just a general recommendation. I know some people in this class can start right away with assembly code, but I do not recommend it in general because I want you guys to focus on the logic and the concept first. Not so much, oh, do we need parentheses here? Do I need a dollar sign here? Do I need a percent symbol here? And so on and so forth. So you don't want to have to handle multiple things at the same time. Deal with the concept first and then deal with the syntax later. Are there any questions? Yep. Yes, because a compare is the same thing as a subtraction. And any addition, any subtraction, any comparison will set or clear the 4 flags that we have talked about simultaneously. So the C, Z, O, and S flags, they will all be affected by the add, subtract, and compare instructions. But you have to remember to utilize the result after a comparison, by the way, because if you space out with an add instruction in between, the add instruction will overwrite the values of the flags. Okay. Any other questions? Ooh, what about this one? How do we compare what EBX points to a particular character? Several things, okay? We all know this is compare, okay? So I don't think any one of you have any doubt about the use of the CMP instruction. Next question. What is the width of the comparison? 8 bits, okay? Very good. What are we comparing to what else? We are comparing what EBX points to, okay? And that means, are we comparing EBX or... It's one of the operands that we have talked about, okay? It's what EBX points to, okay? We have one homework assignment on just that one too, okay? What about quote lowercase o, quote o quote, okay, which specifies the ASCII code of lowercase o. How do we do that in assembly? Same thing, just quote lowercase o quote, okay? So you don't even need to look up the ASCII code. You can just say, okay, I just need to refer to the ASCII code of lowercase o by putting single quotes around it, okay? The next question is, but when you're comparing to that, what addressing mode is the ASCII code of O? Immediate. Okay, very good. So it does seem like you guys have all the pieces. It's just a matter of time to structure the code. If you don't like to deal with CocoaNet to start with, because there's a lot of branches and whatnot, make it easier on yourself. Just look for CO first. Okay? In other words, make it very simple, okay, just to make sure that your overall logic of looping is working first. Just look for CO or just C, okay? Look through the text, look for a single character C to make sure that your code works just for that case. Then add the O, then add another C. By that time, it's just chore to add additional characters. So I would not approach this, like, oh, I'm going to write the entire program to look for CocoaNet all in assembly to begin with. Okay, that would not work very well. But do it step by step, starting with C++ is probably a better way to do it because you already know C++, and just to get the logic to flow correctly is the first step. Okay, we have 3 minutes left. How many people know about revision control? What is revision control? CVS? Anyone? Get, GIT get? Okay. This is one of those projects where it may start to become useful to use revision control. If you do not know what revision control is, you can look it up. And I think one is already installed in this particular distribution. It is called RCS. Nope, it's not installed. Well, you have a virtual machine, so you guys can actually install that. You can install RCS, you can install Get, you can install any one of those revision control software. Okay, revision control is it's also called version control. It's a system that records changes to a file or a set of files over time so you can recall specific versions later. You can also compare, okay? You can say, I want to compare what I have now to something that I checked in 2 days ago. For examples in this book, you can use software source code as files and so on and so forth. Get is, I think, the current standard. Okay, so if you want to use Get, you can install it in the virtual machine. You have to change to super user first, and the password is yours is maybe different. Okay, so you can say aptitude install, just GIT, and I think that should do it. Aptitude install. I misspelled the word. So that will basically bring in, okay, so Get itself is installed. Okay, good. So I can use just Get, which is a little bit hard to use because it is designed to do a lot more than what you need to do as a single developer. Okay, I will give you a scenario. Let's say you're managing a software company and you have software engineers here in China, in Russia, and in many other countries. Okay, so getting together and say, okay, let's work on this program together, is not an option. Physically, you guys cannot get together. And yet, you will have source files where multiple people may need to make changes at the same time. So let's say you have a C++ class that you need to implement. and you divide the job up and say, okay, you implement these two methods, you two implement that method, and you guys will work on the subclass of this particular class and work on that, okay? So all of you will be making changes to about the same source files pretty much at the same time. What do you do about that? Because if the changes are not synchronized, you have a problem, right? Okay? And you can always say, I'm going to email you the file that I have. But that's going to be a problem. Because as you are working on a particular portion of that program, I'll be working on the other portion of the same source file. So when you send me the updated file of yours, I cannot just take that and overwrite my file because my file has certain changes that I'm still working on, and I don't want your file to overwrite my entire file. Is that making any sense? And the same thing goes the opposite way. So let's say that my job is done. Okay, I finished implementing a few methods that I was responsible for, and I say, hey, world, okay, the rest of the development team, I'm done with my part. You guys can now incorporate my code into your working version of the file. So I'm going to email the file to everybody. That's not going to be helpful because all of the other members of the same team, they're still working on their very own version of the file because they have their own stuff to do. But they want to incorporate my changes into their files. What do? Well, they can manually go through the entire file, find out which part I have changed, and delete that portion from their version first and copy and paste my version into their files. They can do that manually, right? What if there are 267 chunks that they have to edit? Do you want to do that manually? No. It can be done. It's just not a very good idea. So what do? You use get. Okay? Git get is one of the many different types of programs that can do this. Basically, it allows you to do version control so that if you're not, when you're not ready to release your changes, but you want to incorporate changes from other people, you can say get update. So what that will do is get will go to a centralized repository and analyze how the code has changed in the repository compared to your working copy at that point. And it will go like, oh, okay, I can see that you have made these changes, so I'm going to keep those changes here. But the rest of the file, you have not changed, but somebody else has changed already. So we'll incorporate the updates of the rest of the file into your working copy. Okay? So it gets kind of complicated. It can do all kinds of other stuff too, like branching a particular program. In other words, you can say, okay, we'll branch the program from version 2 to version 3. Because as you work on the next version, you will continue to find bugs in version 2. And do you tell your customers and say, you know what, we're not going to work on these bugs. Just wait until version 3 is out. Even Microsoft cannot do that, right? They have to keep fixing bugs of an older version of a program until the new version is released. So now you have branching, which means you have to make changes to two different branches of the same program, but they share a really huge base of common code. Is that making any sense? And get can do that as well. And you can mirror changes from one branch to another branch. You can say, oh, we have done all these fixes in Windows 7, okay? And Windows 8 is already, getting worked on. So once you fix all those bugs, you can now say, I want to reapply the same bug fixes into version 8 of Windows, and get can do that as well. So it's a very useful kind of tool. It's kind of complicated. I think by itself, it's kind of like a one unit class, can easily be a one unit class. But if you only use it as a single user, and you are the only one who is doing changes to like 1 or 2 files, you can probably read the tutorial on get. Okay, just look for get tutorial and learn how to use the basic stuff in 15 minutes flat. Okay, and I can tell you that 15 minutes is good investment because you will find this tool to be useful not only in this class, but in every single class that you have to deal with source code. Okay, so that's all I have to say. It's up to you guys to decide whether to use get or not. It's just useful in general. I will go to the lab later, so let me stop the recorder first.